So we have a gas mixture having a molar analysis of 70% carbon dioxide and 30%, what is H2? Hydrogen. Hydrogen. All right. It enters an insulated compressor. So here's a compressor. Comes here, goes out. It's well insulated, but you know it's going to take some power or work to drive that compressor. Let's put it as W dot power. It comes in, and it's some carbon dioxide, and it's some hydrogen. Well, how do I represent the fact that they give me this molar analysis of 70% CO2? I would say Y of subscript CO2 is equal to 70%. True? And Y of H2 is 30%. If I add that up, is it 100%? Yes. The compressor operates at steady state. It comes in at a pressure, let's say this is inlet state 1, of 100 kPa. And a temperature, inlet 1, 20 degrees C, but I suspect there's some entropy calculations. Let's get that temperature right away in Kelvin. 293 Kelvin. And they have a mass flow rate, m dot, of 2.5 kilograms per second. All right? Is this mass flow rate the mass flow rate of the mixture, or of the CO2 in the mixture, or of the hydrogen in the mixture? Which is it? It's of the total mixture. All right? Now, you're going to have to know the molar masses to switch back and forth between a molar basis or molar description of the problem and a mass basis or a mass description of the problem. Let's continue to read the problem. A lot of students like to stay in the mass description if they can solve it that way, completely using masses. Or they'll switch with a little arm twisting after they get more familiar with the molar description. It's compressed to a pressure outlet 2. The pressure at 2 is 1,500 kilopascal. Make sense? The isentropic efficiency of the compressor is 80%. For carbon dioxide, use this value of specific heat, this value of C sub P and C sub V, okay? And use this value for hydrogens. Now, when you're given these values of specific heats, what does that say? How do I interpret that? Don't go to the tables. You just use those simple analytic expressions for the changes in H if I need it, or changes in U, or changes in S if I need it. All right. Determine the exit temperature in degrees C. So how are we ever going to get the exit temperature in degrees C for this problem? We're trying to find T2. Let's worry about that first, then we'll look at B and then C, okay? How would I solve for the exit temperature? Do a control volume analysis, okay? With a control volume, I'll do a first law. With the first law, I'm going to try and write it over here because I know I'm going to run out of space, okay? Would I have something like this that says that W dot into the compressor, that's into the compressor, the arrow is showing into the compressor, is equal to the mass flow rate times the enthalpy exit minus the enthalpy inlet. That look reasonable? For an ideal gas, can I replace the change in H by C sub P, T2 minus T1? Let's check off. Do I know T1? Do I know m dot? Do I know specific heat of the mixture, C sub P? A little bit of work. I have to do a little bit of work to get it. I know C sub P of each of the components of the mixture, but I need to get the specific heat of the mixture. And T2, I don't know it, but I have to do some work to get it. Okay, so how about the specific heat of the mixture? C sub P of the mixture. Now, sometimes I'll explicitly put MIX, but this textbook doesn't like a lot of long subscripts. And so I'm tempted to always put mix on it, but when you don't see a subscript, it means it's for the mixture. C sub P for the mixture. Well, I need this not on a molar basis, but on a mass basis. And a little bit of algebra shows that it's equal to the sum of the mass fractions of each component times the specific heat of that component. True? Okay, I've got the specific heats per unit mass for each component. I got to get the mass fractions. How do I get the mass fractions? I use the molar fractions. And so I set up a little table to help organize the work. So I'll set up a table and I'll say, okay, what component do I have? Well, I have component CO2 and I have H2. And what is the reported mole fraction for that component? 70% and 30%. At this point, what I'm going to say is I'm going to assume N is equal to 1 kilomole. If that's true, how many kilomoles of CO2 do I have? See what I'm doing? I'm saying I know Y is 0.7. If I say N is 1 kilomole, then how many kilomoles of CO2 do I have? 0.7 and 0.3, and you sum them up and it's 1 kilomole. So N total is 1 kilomole. It's kind of redundant there. I know that. But now that in my mind I know that I started with 1 kilomole of the mixture, and I'll have 0.7 and 0.3 kilomoles of this component and that component, if I knew the molar mass of that component, what is the molar mass of CO2? 44.01. I look it up in the table. It's around 44 from memory. Carbon, 12. Each of the oxygen, 16. So 2 times 16, 32. Add 12, 44, with some change from the table. Okay? And what are the units on this molar mass? First and only clicker question for today. Don't call it out. Molar mass has units of kilograms per kilomole. Answer A, or kilomoles per kilogram. Let's go ahead and start our response. I know that for the CO2, I said, oh, it's 44.01. But I get confused on the units. So is it 44.1 kilograms per kilomole? Answer A. Or 44.1 kilomoles per kilogram? Answer B. Ed, show the results. Congratulations. Congratulations. So there you go. So if you want, put up in the header that this is kilograms per kilomole. So what is it now for the other hydrogen? Well, it's 2.016. Hydrogen's an itty-bitty little molecule compared to the massive carbon dioxide molecule. Okay. Now, what I do is I say, if I have that many moles with that molar mass, guess what M is? I take the product, don't I? What's the product of Y times the molar mass, or N times the molar mass? Well, I'd have 30.81 kilograms. And I would have 0.60 kilograms. I add it up. I have 31.41 kilograms. So if I started with 1 kilomole of the mixture, I would have 31.41 kilograms of the mixture. True? And I could say the mass fraction of that mixture comes in where the vast majority, 98.1%, is carbon dioxide by mass. And only 1.9% by mass is the hydrogen. But look at it. Look at the mole fraction. It was 70% CO2. Now it's 98.1% CO2, right? Because CO2 is so heavy, it has a lot greater mass fraction than it does mole fraction. Can you tell me what is the molar mass of the mixture? 31.41 kilograms per kilomole of the mixture. That's the molar mass of the mixture. Make sense? All right, so I had the molar mass in a mixture, but I really needed those mass fractions. Here are, so what I have is I have 0.981 times the specific heat constant pressure of CO2, 1.014 kilojoules, I'm going to leave the units off, plus 0.019 times 14.513. And so I'm going to pick it up here. I'm going to kind of try to save space. Sorry about that. I'm going to pick it up right up here. I'm going to have that the specific heat of the mixture, C sub P of the mixture, is 1.2739 kilojoules per kilogram Kelvin of the mixture. Make sense? Okay. How about now T2? I had to do some work to get the mass fractions, to get the specific heat of the mixture. So I'm kind of checking through this. That's now check. I need T2. How am I going to get T2? Yeah. So what I need to do is I need to think about isentropic work and then modify it using the 80% isentropic efficiency. So if I was able to isentropically compress it, could I use an equation like T2S is equal to T1 times P2 over P1 to the K minus 1 over K? It's an ideal gas mixture. Oh, but what is K? 1.4, but that was for air, diatomic. We don't have a diatomic. We have CO2, triatomic, and hydrogen, just a simple H2. I have to get, just like we got the molar mass of the mixture, the specific heat of the mixture, I need to get the K of the mixture. If I went and got C sub V of the mixture, it would be 1.0091 kilojoules per kilogram Kelvin. If I knew C sub V of the mixture, C sub P of the mixture, can I get K of the mixture? Ratio of specific heats. And so the K of the mixture comes in at 1.2323. It's close to 1.4. It wouldn't have been far off from 1.4, but there's a better number right there. Okay? So if I stick that in, I can find that T2, assuming isentropic compression, notice that I have to put in 293 for T1. I come out with 514.4 Kelvin. But that's not T2 actual. T2 actual is going to be greater or less? Clicker question. T2 actual is going to be greater than T2S, answer A, equal to T2S, answer B, or less than T2S, answer C. So I'll start it right now. And it just started, okay? So you can enter your answers. The actual temperature, which is it? Is it greater than 514.4 Kelvin, equal to it, or less? Let's go ahead and stop it. And let's take a look at the results. Well, the efficiency is given to be 80%, so it's not going to be the same. If it was 100%, it would be the same. True? If it was efficiency, isentropic efficiency is 100%, it would be the same. Now, because it's less than 100%, and the isentropic efficiency will never be greater than 100%, not in this textbook. Maybe some scheme somewhere somebody talks about efficiency greater 100%, but engineers start to cringe a little bit, right? I can't do that. I can't give you more than 100%. So it's going to have to put in more work. And if you put in more work to boost the pressure up, that's what a compressor is trying to do, then it's going to make it hotter when it goes out. So the actual temperature would be greater than the isentropic temperature. Got it? That help in the logic? So what you find is that T2 actual will be equal to T1 plus T2 isentropic minus T1, what the temperature change would be divided by the isentropic efficiency of the compressor. I unraveled the efficiency equation. I'm trying to use space wisely and skip a couple steps, but hopefully you've solved enough problems to say, yep, that's right, that looks good. True? So this temperature, T2 actual, comes in at 569.8 Kelvin. So right there, we finally got T2 right there. So that was actually our final exit temperature. Let me put it up here. T2, you subtract off the 273, and you get the T2 is 296.8 degrees C. Now, what about that exit power? W dot compressor is equal to the 2.5 kilograms per second times the specific heat, 1.2739 kilojoules per kilogram Kelvin, times the temperature change, 569.8 minus 293 Kelvin. And the units work, W dot compressor, turns out to be 176 excuse me, 176 kilowatts. Did that help? Let's take a look. Rate of entropy production. What symbol am I going to calculate for this? Sigma dot. Look at the units. Did the units look good? Yeah. Kilowatts, that's a rate per Kelvin. Kilowatts per Kelvin. That's rate of entropy production. True? How am I going to solve for sigma dot? Second law, control volume around the compressor. And I'm going to try and do it in this little space left, but I won't be able to do it. So it'll be something like sigma dot equal to the mass flow rate times S exit minus S inlet. There's no heat transfer. There's no entropy transfer with the work. It's steady state. Look good? Entropy balance give you that? I know the M dot. I just need to get the S delta S. So would the delta S be something like C sub P natural log T2 over T1 minus R natural log of P2 over P1? Okay. Two things. One is I can do it for each one, or I can say this is C sub P of the mixture and that's R of the mixture. That's a little slicker if you do it that way, but look, it'll work that way as well. So if I say I need the C sub P of the mixture, already have it. How about R of the mixture? It's going to be R bar divided by the molar mass of the mixture, which we calculated. True? We calculated it to be 31.41. Guess what? Then I can use the total pressure of the mixture on the outlet, the total pressure inlet, the temperature outlet, temperature inlet. Did I write this equation correct, or should that be a plus sign in front of this R? Is it a minus sign in front of the R? It's a minus sign in front of that R. Okay. So really, I almost did it. I almost stayed. Let me try and see if I can stay to one page. Not really. I got to scroll down just a little bit. Sigma dot, when you substitute the numbers, 0.0652 kilowatts per Kelvin. 0.652 kilowatts per Kelvin. True? How many significant digits is that number represented to? 3 or 4. One is incorrect and one is correct. It's 3 significant digits. Okay. Let me ask this question. What is the rate of exergy destruction in that compressor? T naught times sigma dot. You got it. So multiply. I didn't do it. I just asked that question. 298 times that. Okay.